Greetings from New York City and Columbia Business School, Executive Education. I'm Scott Gardner. I'm here today with Professor Assaf Zeevi for the Data Science and AI and How They Are Shaping the Business Landscape webinar. Before I introduce Professor Zeevi, I'd like to just go over a few quick logistics. If you'll look at your screen right now, a recording of this webinar will be made available to you. If you'd like to tweet about this webinar, please do so at #CBSExecEd. And finally, most importantly, please submit those questions to the Q&A box. We'll get to as many of those as possible in the last 10 minutes. It's my pleasure to introduce Professor Assaf Zeevi. He is the Kravis Professor of Business at Columbia Business School. His research and teaching interests lie at the intersection of operations research, statistics, and machine learning. He has received several teaching and research awards, including the Career Award from the National Science Foundation, the IBM Faculty Award, and the Google Research Award. He also serves on various editorial boards and program committees in operations research and machine learning communities, as well as scientific advisory boards for startup companies in the high technology sector. Professor, it's great to be with you today.
Thank you very much, Scott. Pleasure to be here.
Thank you. I'm going to leave the stage. I'll join you for the last 10 minutes for questions. But before I go, just tell me, to get started, let's talk about the connection between big data and AI.
Thank you very much, Scott. I'll exactly lead with that point. So as the first slide here shows you, we're going to start off our discussion centered on data. Data, in a way, is a big driver for the developments in the AI space. So we used to think about economic activity as being predicated on traditional things like labor, land, and capital, and we see in recent years the emergence of data as the fourth pillar in that new economy. And you have a sense from some of the numbers on that slide, what are the extent of data generated today, many of them on the web, but also in other various sectors, including, for example, healthcare, which is mentioned there, and future frontiers like autonomous vehicles. And it is mind-boggling to think about the amount of data we're accumulating and the fact that 90% of the data today that we have is essentially generated in the past year. So this is really a revolution. How is AI connected to this world? Well, you may have heard the term big data. So there's this notion of what we can do with data, which is where AI steps in. And what we can do is explain things like what has happened using data. That part is called descriptive analytics. And why did it happen? Finding explanations, that is more about diagnostics. Whereas the frontier that we're sitting in right now, transitioning into, is what's likely to happen, which is predictive, and what should I do about it, which is prescriptive. That is the ultimate challenge here, and this is where we feel that AI has the biggest contribution to make in this space. So isn't AI just statistics? At some level, the term is used so heavily now or overused to the point where you want to make a distinction between what exactly is AI versus traditional disciplines like statistics. So in many ways, these things are similar, and when you actually reduce AI to its key components, many of them actually originate in statistics. But there are many things that make AI unique. First of all, many of the things that are generated by AI models and algorithms are of the black box variety. We don't really know what's inside, but we know that it can actually mimic a certain activity that we're interested in. And it certainly has a much more algorithmic nature than statistics. So it's more interdisciplinary. And in particular, it leverages heavily this integration between how to represent a certain problem, how to optimize it, and then how to use computational tools to solve it. So it's a broader scope that I would say encompasses also big major elements from statistics within it. So let's start off with a really simple example to explain some of the challenges as we move toward the discussion of AI. How to explain the difference between an apple and an orange. But think about that, for us as humans, is a triviality. We learn that at a very young age. But if you try to thinking about teaching that to a machine, you have to deconstruct these objects into more basic primitives. For example, using features like size, shape, weight, color, and only some of these features really capture the essence of what this distinction is between, in this case, an apple and an orange. But how to find these distinguishing features? That is definitely one of the big challenges for AI engineers to come up with, is feature extraction and identification. And you can see if the problems get very large, this becomes critical. Take, for example, the problem of identifying a web page in a response to a search query. You see here some numbers about the number of pages that are indexed today by Google. Finding something in that mass of data is very complicated. So these features are critical in explaining to an algorithm how to do that. There are some other numbers here that you see, as well as one that probably is used very heavily as an example is in online retail. Companies like Amazon and others sell enormous range of products today. Just recently in 2017, we sort of crossed the line where there was more shopping done online than actually in stores. So this is, whether we like it or not, the future. But how to actually work that enormous amount of items and sort through them, and how to make some recommendations. This is a very challenging problem, and we'll seg to further examples. We'll see that it's even harder when we try to do this in real time. In the case of online retail, here's a simple example. If I search query for earphones, or headphones more generally, then there are about 30,000 different such headphones sold on Amazon. Ultimately, when you search for this on a computer, or if you use your mobile, it's even more challenging. We can only display a very small number of these on the screen. But which ones to display? This is a very hard problem to choose among these many items, the ones that are most relevant to a particular consumer. And it's one of the problems that Amazon tackled very early on and is very well known for, solving this by means of what's known as a recommendation engine. So this is one of the very first instances of AI-type technologies that have become very pervasive. And the idea is that you use these salient features of the products, as in that apple-orange example, to identify what's common and what's different. But you incorporate many different things that have become some of the elements of the secret sauce that makes this work so well, like user reviews and ratings for these products. Various patterns that we observe over time of how users substitute one item for the other and how their preferences are organized. So the consumer behavior here plays a very important role. And most importantly, in these settings, we actually get a response from the consumer. That is, we show the consumer the subset of headphones that we feel are most relevant, and then either they choose one of those, or they continue searching, or they just leave. This reaction, let's say, to simplify it, just think about a click or a no click on that, is very critical in terms of feedback to train our algorithm. This is the first layer of AI, which is known as supervised learning, because we see examples that are labeled. Our algorithm can work with an example that's actually labeled by seen a previous response or have not seen a previous response. We're going to move into more complicated settings now. One of them is in healthcare. Healthcare, traditionally, if you think about healthcare investments, they have been done mostly in the area of pharmaceuticals and devices. But there's an emerging area now which is revolving around analytics and leveraging the big data revolution and AI. And out of the many examples that I've listed on the slide, there are many of them have very important societal benefits to them. One of them is managing hospitals in a more clever way. So the model of a smart hospital, how do you construct that? Well, we go again, as in that previous diagram, from the descriptive, which is thinking about things like the length of stay of a patient in the hospital, mortality rates, readmissions, and so on, to the level of diagnostics. Can we use this data that we accumulate to explain various sources of complications for the patients, or bottlenecks that exist in resources in the hospital, nursing staff, physicians, etc., to the point where we want to do predictive analytics, which could detect deteriorations in real time and discharge readiness for patients. And ultimately, as I mentioned earlier, the real challenge here is to go to the prescriptive. Real-time interventions, real-time resource allocation, something which seems at this stage to be very far off from what our capabilities are, but I'm going to indicate that we're heading in that direction. All of this requires a very high level of accuracy, but also interpretability, because in many fields, and two examples I'll talk about here with a little bit more detail are the healthcare analytics example, and subsequent to that, autonomous vehicles. These are examples where there are a lot of legal repercussions, and interpretability is very critical for adoption in these industries. So I'll show you an example where the future is almost here. This is an actual system that is running and undergoing trials today in a hospital in the US, which is tracking patients in real time in an intensive care unit. This is the most complicated unit in the hospital because the patients are in such acute condition and requiring very high-touch care. So without getting into too many details of what's on the slide, the topmost graph shows you this jumble of information that's obtained from multiple sensors and monitoring devices, ranging through lab results and so on. And ultimately, two very important indicators are in the one graph below that have a green and orange colored graphs, which show essentially the oxygen saturation in the blood and something called the lactate serum, which is essentially an indication of stress on the body. And the most important punchline in this slide is that under very expert physician supervision, it's very hard to pick up from all this jumbled up signals a clear indication of whether the patient is deteriorating or not in real time. And that's because the human brain is not very good at integrating very high dimensional input spaces like these signal spaces. But there is an AI algorithm that runs in real time, and as you can see in the bubbles there, is able to detect a deterioration that occurred several hours in advance of what was actually recognized by the treating physicians. And in the second graph from the top, you can see the deterioration formed in the fact that the green curve, which is the oxygen levels, have dropped significantly, and the other one, which, as I mentioned, is the lactate serum, has risen significantly. These are indications of extreme stress on the patient. So the ability to actually do this in real time and take all this very complicated signal space and translate it into something which is interpretable is almost within reach. And how do we do that? This is a form of learning which is often referred to as semi-supervised. Why is that? Because we're giving the algorithm some help. We're actually building a system in which various features of the ones that I described earlier, like the orange and apple, are being pre-baked by knowledge, which is part of the domain expertise that physicians have. Like, look at the following things and give more weight to them. So we construct this architecture in a way that we take this raw data coming from multiple sources, we have to make it all accessible to the algorithm, and then we have this concept that appears on the slide called primary concept, which is essentially this very complicated feature extraction process that I was alluding to earlier with the apple and orange comparison. And through that, we have a machine learning algorithm that actually does the predictive part of it. But the challenge is, again, to do all of this in real time, where a lot of this monitoring is done at a very frequent basis, and where the condition of the patient can change quite a lot from even within intervals of 10 to 15 minutes. An even more extreme case, if you wish, is the challenge of teaching a car to drive. So in this context, again, we require very high levels of accuracy because mistakes are going to have disastrous outcomes, and interpretability. So as I was alluding to earlier, a lot of the AI distinguishing algorithms are so-called black box. That is, you feed something in, you get something out. You feed camera information in, and you get out some signal about what to do with the steering wheel or the brakes. But if you then deconstruct this, the regulator at least needs to know if there was an accident, what happened. Insurance company would want to know that too. Eventually somebody's going to be responsible. And in this case, there is no someone, it's an algorithm. So how can we achieve that? These are snapshots on this slide that are taken from an actual system that's being tried and tested today. And you can see an element of what the system sees, quote unquote. Those are those green silhouettes over the cars, and how it looks inside the vehicle and the command and control post, which actually does all this tracking. And you see that there's an importance of distinguishing various features in the landscape. Vehicles versus pedestrians is very important. A traffic light, signals, etc. Various things that relate to the weather conditions and so on. Multitude of input signals that have to be integrated and then formed into these distinguishing features that can separate, again, car, pedestrian is like the apple and orange in the previous example. Not only do we have to do that consistently in these types of nice weather conditions, we need to do this also in situations where visibility is much less conducive to the algorithm. So here is a situation where we're at nighttime and we still can recognize the vehicles and distinguish from pedestrians very well. The problem in this space that I want to emphasize to you, which is again one of the reasons it's on the frontier, just like the healthcare example, is that there are way too many possible scenarios to train on. So if you think about historically how we would program a game of chess or tic-tac-toe, which is sort of an exercise you do when you start to study computer programming, the tic-tac-toe at least, then we don't have that many scenarios to consider. That's why we all learn to master tic-tac-toe pretty quickly. But here the number of scenarios is basically close to infinite. So we can't just feed the algorithm all these inputs and expect that we can label them and get a good outcome like we can do, for example, in that e-commerce example. There are too many rules to encode. It's not like chess where you have a certain number of pieces, each one moves according to certain rules. So how to deal with all of that I think led to the development of the most exciting frontier of AI, which is autonomous unsupervised AI. Unsupervised because we can't actually label things as 1 and 0 like that e-commerce example, or the patient be deteriorating or not. Things are much more ambiguous here. And at the same time, we have these challenges that are related to interpretability. In this space, you'll hear the term deep learning used. It is actually one of the most fundamental premises of running things like autonomous vehicles, with the challenge of interpretability. So we're really here on the frontier. And to go back to that example of distinguishing features, think about this situation here that the AI layer has caught, which is essentially an object that's bouncing on the street. You see the object hasn't yet been classified. The coloring there hasn't yet been classified into one of the objects, which is beware, slow down, accelerate, etc., because it takes a while for the algorithm to pick up and understand what that is. Is it an apple or an orange? Is it a baseball or a basketball? And because these things look very different, we can spot them immediately, but to an algorithm, to train them, the algorithm to actually react to that appropriately and understand what's what is one of the biggest challenges. This is why this term of unsupervised autonomous AI is used in this context and why it's been such a successful technology. It's not been rolled out yet, but it's a very successful technology with a promise to solve many other very fundamental problems. And just to give you a glimpse of what's happening, so to speak, under the hood, if you look at this challenge of designing the autonomous vehicle with this AI layer, there's a whole set of the mechanism which is just acquisition of information, just like we had in the patient monitoring example, which then feeds into what's labeled in this diagram as narrow agents. These are small AI entities called agents, each responsible for a certain layer in the problem, because the problem in totality is just too complicated to solve. So it's been deconstructed into sub-parts, each one having its own agent. And you can see the control. This agent recommends certain actions as this car is entering a curve, like slowing down, maintaining a certain degree of rotation in the steering wheel, etc. And these are translated into actual actuation commands to steer and control the vehicle. So an extremely complicated problem, one that, again, we have not fully solved yet, but for which the technology is starting to be quite ripe for initial implementations. And I think, like many things, like the first major missions we had into space, this is going to create a whole slew of technologies that will revolutionize many other aspects of other businesses. This is simply the one that's driving a lot of this development right now. So that's, with that, I'd like to sort of end the formal part of the slides to leave enough time for the Q&A, and I'd like to invite Scott back up to help me manage that part of it.
Yes, absolutely. Thank you very much. This is really fascinating information, very interesting information you've got here today, and very robust also. So we have some wonderful questions that come in. Would you like to answer a few?
I mean, I can try.
All right, great. These two came in, and I feel like they really kind of correlate with each other. So I'm going to, if you'll allow me, I'm going to ask both of them together. They're from Santiago and Charles. Santiago asks, what are the capabilities that senior talent should focus on to thrive in leadership roles for AI and data science? Charles, correlated to this, asks, what are the most important practical skills non-technical executives should learn about AI, and how will it be applied?
So those are great questions, and I thank the audience again for participating and providing these excellent thought pieces for us to chew on. I would say that primarily the most important thing for an executive in this landscape is to understand what are the limitations of AI, because you hear the term now thrown around on pretty much everything. We have a problem, we can solve it with AI, right? I don't think that's true in a lot of cases, and even if it is, the amount of customization that has to take place, and I was trying to indicate that a little bit with this autonomous vehicle example in contrast to the medical monitoring example, the amount of customization is significant. It's hard to imagine a one-size-fits-all solution here. So for an executive, primarily the question is, what can I do? What's achievable? And the second thing to operationalize this is, do I have the DNA in my organization to actually set this up internally, or do I go externally? And if I go externally, where do I go? Because again, this is an emerging field. We don't have fully mature solutions out there you can plug and play. As I said, customization is a big element here. So to me, those are the two most important things to ponder first if you're an executive in this space.
And I would also venture to say that, just the idea of why am I asking for this need? Am I just saying because I want AI and I want to move into this realm, or is there really like a true need for this in my company that can't be met with other methods?
That's a great point, and I think, again, it's good for the audience also to consider a distinction between things that are automation and AI. If you go to the airport and you see less and less of the border control officers, it's because we can automate some of those aspects. But those systems may or may not rely on AI. They don't have to, and many of them don't. To control your luggage and get it transported to the aircraft, you don't really need sophisticated AI systems. It's really just automation. So these are really two different things. Automation is easier to achieve. The AI layer is much more challenging in many contexts.
And do you think it's a path from automation to AI, or sometimes some things will just be that's an automated. Don't put your money there.
I think some things are just ripe for automation, and some things are going to be commoditized, like certain services that we're seeing more and more. But AI solutions, again, in my presentation, I focus on things which are really more on the frontier to give you a flavor of what's going on there, and hopefully we'll have follow-ups to this where we're going to dig more deeply into various verticals and that use AI. But it's a big investment. It's one of my main takeaways here. A very massive investment to actually develop these types of capabilities and customize them to a specific problem. And to me, that would be one of the first things I'd be focusing on.
Yeah. Okay, great. All right, two more questions came in that I feel are a good, correlate to each other, from Leroy and Oksana. Leroy asks, how can organizations address this changing landscape while still meeting today's priorities? And then Oksana asks, how can I scale the basic knowledge of AI and ML across all levels of my organization?
Those are really good questions too, and they're a little bit more open-ended, so a bit more difficult to answer. I would say that in an organization, one of the things, and I'm taking the second question, one of the things that I think is really important to understand is where, if at all, do you focus an AI-oriented activity? It's not clear that this is something that you want to do at all levels of organization, as so was a subtext of that question. There may be, and for that, it's really important to understand what's the flow within the organization and what could be a bottleneck that AI could come and solve. So a really good understanding of the organization and understanding where the AI layer is needed is important because, as I said, AI solutions tend to be high touch in terms of customization. So normally you'd like to have maybe one or two of these where you put a significant effort in developing an AI layer that would really boost your organization's productivity, but you don't want to do this in a very widespread manner because the investment is very large, and I think in many cases the return you're going to get for the investment is not going to be worth it.
Right, right. All right, Santosh asks, what are the promises of AI and the pitfalls to avoid?
That's a great question too. So the promise is really huge. As I showed you again in this talk, a few examples of what are the possibilities for things that I think 10 years ago would seem pretty much like science fiction and are becoming more and more a reality. So the promise is very large, but with it are a lot of issues that we have to worry about. So I alluded to this in the autonomous vehicle example. Ultimately, you will have these vehicles that are completely run by an algorithm. But if something happens, who's responsible? Who's to blame? An algorithm, that doesn't seem like a very satisfactory answer, especially to us as human beings. So there are questions like that. There are questions of fairness. Are we actually crunching all this data and providing a bias to the algorithm? Think about implementing this type of system in a judicial context, which is one of the things being considered today. A lot of the history of cases and rulings have an embedded bias. We will embed the bias in the algorithm through these various learning mechanisms that I discussed, like supervised learning, where we have the outcome of the trial and we train the algorithm based on input and outcome of trial. I worry about those biases becoming a very significant issue down the line, because again, it's an algorithm, it's not a human being, it's not a judge or a jury. So these are things that we have to be concerned about.
Yeah, that seems like it would be a huge concern. Okay, so on that level, Adi has asked this very interesting question: is there a plateau in terms of available data and AI? AKA, as we gather more data, will AI become smarter in a linear way, or are we finding that the 1 billionth piece of data is not making our AI smarter? And I think I was listening about compartmentalizing sections, but that's a good question.
It's a very good question. We're very used to seeing that in other domains of business, like the concept of economies of scale. We're used to thinking about scale as being something that gains a lot and then eventually tapers off. Like beyond a certain point, you're not really realizing scale in the same way that you were initially. And to some extent, the same is true about data. I think it's very context dependent. To go to the examples that I presented here, if you think about that medical example, I say we're not close yet to that plateau that Adi was talking about, because the human body is so idiosyncratic that we need as much data as we can to draw these inferences that we're making as in that algorithm, or if we're going to manage more effectively chronic diseases like heart conditions or diabetes and so on. That idiosyncrasy is really one of the difficult challenges. In other examples, when we think about facial recognition, we have reached saturation. We can do that very well. We don't need to accumulate the billionth data point that she was alluding to and improve the algorithms.
It's hit its plateau.
It's hit its plateau already, I would say.
Okay, super. So this is, do you think, and this for people who are running companies and people who are thinking about this, again, I think this is a concern for them. Do you think technological development is outpacing the capacity for firms to implement? And if so, what do you think will be the consequences for that?
I think that's I hate to repeat myself to say everything's a good question, but that's also a great point. I think that in general, when you consider the evolution, especially in the AI space, it's been very rapid, and it's to the point where I think we're seeing more and more companies trailing behind and having a hard time keeping up. And because there are not ready-made solutions, plug-and-play solutions to this, it's not like you can download a new version of a Word editor or something and get that to work. It's becoming a significant challenge for many companies to keep up with it. And many of them are looking for solutions, AI-oriented solutions, but it's not clear where those answers will come from. I mean, there are a lot of startups in this space, but they're, again, developing fairly customized solutions because of the difficulty I was alluding to earlier of developing a one-size-fits-all solution. So we're definitely seeing that. I don't know what's going to be the consequences, but it is one of the big challenges in this space, especially for executives and companies that are considering whether to introduce these technologies into their organization.
Wonderful. Well, we've got about a minute and a half left, and I think this is a great last question. Two things. How would you measure the success of AI initiatives, and then where do you see it in 10 to 20 years?
It's another good point about measuring success. So I think if you take, at least let's say one of the examples that I showed was this online retail example. I think the success of online retail is not controversial, but it's due to many sources, not just AI, also the great logistics operations and so on. We get these packages delivered in 1 or 2 days. It's amazing. Autonomous vehicles, I mean, where we thought it would be easier, it turns out to be harder than what we thought to achieve the full level of autonomous vehicles. And it's not clear how to introduce and what's going to be the adoption and so on. So many things here are a bit in flux. I would say 10 years from now, we're going to see a major revolution in certain industries. Definitely, I'm talking about logistics, distribution, drone deliveries, autonomous vehicles. All of these will become reality as healthcare monitoring. All of this will be a reality. But in many other areas, I don't know if we're going to reach actually full fruition in terms of the AI initiatives, because the problems will turn out to be more challenging than what we thought.
Right, right. It's just constant evaluation of that, right? Thank you. This was terribly interesting. So thank you very much for being with us today. Thank all of you for joining us, and we'll see you again soon.
I wanted to thank the participants as well for being online. It was a pleasure to have this opportunity to speak to you a little bit about these exciting topics.
Thank you.